Hello everyone. Today we are back with a new series of algorithm which is unsupervised machine learning algorithm. In this video we will discuss about the type of unsupervised machine learning and pick one type of unsupervised machine learning and discuss it in detail. So before we start, here are a few details about DataMonk. In DataMonk, we help students to prepare for different type of interview and also provide study material on SQL, Python, statistics, case studies, and machine learning. And if you want to know more about the DataMonk, then you can visit our website www.thedatamonk.com. So let us start with the unsupervised machine learning. What do you mean by unsupervised machine learning? So basically, as the name suggests, unsupervised machine learning means that it is the model without any intervention. Like in this algorithm, we do not need any supervision to learn about the data. It means that you do not have to explicitly train them by telling this is the input X and this is the input Y. Unsupervised machine learning is about finding the pattern in data by just passing the full data to the algorithm. So there are three major types of unsupervised machine learning. First is clustering, second is dimension reduction, and third is association. So for clustering, we group similar type of rows, and for dimension reduction, we group similar type of columns. And in association, we find the association between the data. So in clustering, there are four type of algorithm. First is k-mean, then hierarchical, then DBSCAN, then optics. In dimension reduction, we have five type of machine learning algos, which are factor analysis, PCA, ICA, TSNE, and UMAP. And for association, we have three type of algorithm, which are a priori, eclat, and FP growth. So now you know about the clustering, dimension reduction, and association. So in today's video, our main focus will be on clustering. We will discuss every type of algorithm like k-mean, hierarchical, DBSCAN, and optics in detail with their hyperparameters. So first of all, what do you mean by clustering? Clustering is the task of dividing the population or data points into the number of groups such that the data point in the same group are more similar to the other data point in the same group than those of the other group. In simple words, we say that the aim is to segregate with similar traits and assign them into the clusters. Let's understand this with an example. Suppose you are the head of the rental store and wish to understand preferences of your customer to scale up your business. Is it possible for you to look into the detail of each customer and devise a unique business strategy for each one of them? Definitely not. But what can you do? Is to cluster all of your customer into say 10 groups based on their purchasing habit and use a separate strategy for customer in each of these 10 groups, and this is what we call clustering. So now you should know the definition for clustering, but how can we use clustering in our machine learning algorithms? So we have four type of machine learning algorithms in clustering, which are k-means, hierarchical, DBSCAN, and optics. So let us first look into the k-means. K-means is one of the most popular algorithm in the clustering. K-means algorithm is simple yet powerful unsupervised machine learning algorithm. It is used to find groups, clusters of similar rows in our data. The working of the k-mean is very simple. We just have to pass the data and tell how many clusters we want, and k-means will automatically assign a group to every row in our data. So now let us see how does the k-mean work. So for k-means algorithm, there is only one hyperparameter, which is k. And if we assign the value of k equal to 2, then we need to find only two groups in our data. Then after assigning the value to the k equal to 2, we have to assign group 1 or group 2 labels to each observation in the data randomly. Then after that, we have to find the center of all group 1 points and all group point 2, and these centers are known as our centroids. Then after choosing the centroid, we just have to find the distance of each point from both the centroids and assign each point to the nearest centroid, hence the corresponding group. And how do we find the distance? We find the distance by Euclidean method or Hamming distance and other distance formulas. So this is the basic algorithm how k-means work. We just have to repeat this step for further assignment and we can find the groups of our data. So let us take a look into the image to find more about the k-mean. So this is the k-mean working. Like you can see, we have randomly assigned the group to group 1 and group 2. Then we have chosen the center for both the group like this one, and they both are known as our centroid. Then after that we will find the distance of each point from the center. Like this is our point. We will find the perpendicular distance from the centroid. First we will find the distance from the centroid, then we will find the distance from the centroid, then we will choose the minimum distance and assign it to the group. So this will be our minimum distance. So this belong to the cluster 1, same as this. Like first we will find the distance between this and then this, then assign it to the minimum distance. So this data point will belong to the group 2. So the working for the k means is very simple. We just have to assign the value of the k and then make the groups and find the clusters. But how do we find the perfect value for the k? So to find the perfect value for the k, or find the optimal number of groups in our data, we find it by running the process iteratively for k equal to 1, 2, 3, 4 till 10 and note down the withenness. The similarity between all points within a group. This is measured as the sum of the distance of each point from the centroid. This is also known as our inertia. If all the points are close to the centroid, that means that the group is homogeneous. All observations are very similar. Ideally, withenness should be 0, but in practice, we try to keep it as low as possible since you never get the 0. And for the distance between the points, Euclidean distance is very popular for the withenness calculation or inertia calculation. So that's all for k-means clustering. Now we will look into the hierarchical clustering. Hierarchical clustering is another algorithm that helps to group similar rows together. In hierarchical clustering, we have two types of algorithm. First is bottom-up approach, agglomerative. Second is top-down approach, divisive. So let us first look into the agglomerative clustering, which is a bottom-up approach. So the working for the agglomerative clustering is that we assume that every row is one cluster in itself. So if you have 100 rows of data, then we will start at the bottom with 100 clusters. Then after choosing the 100 cluster, we compute the distance metric of each cluster from every point from every other cluster using the distance measure, Euclidean or Manhattan. And for text and other non-numeric data, we use Hamming or Levithan distance. So after that, we use the above distance metrics to calculate the distance between the clusters. The cluster distance can be of three types: single linkage, complete linkage, and average linkage. So for single linkage, it is the shortest distance between these two clusters. And for complete linkage, it is the largest distance between the two clusters. And for average linkage, it is the average distance between the two clusters. Let us look into the figure to understand the three type of cluster distance. So as you can see, this is our single linkage which calculates the shortest distance between the two clusters. As you can see, this will be our shortest distance between the cluster R and S. And for complete linkage, it is the largest distance between the two clusters. So as you can see, we have computed the largest distance between the two clusters R and S. And for average linkage, we have computed the average distance between the two clusters. So we have computed distance for every cluster and then find the average for that. Then after finding which cluster are closest to each other, we combine all those clusters that are closest to each other, and we keep repeating this step till only one cluster is left. So now you should be wondering, then how can we find the optimum groups or cluster? So to find the optimum groups or cluster, we use the dendrogram. So let us look what do you mean by dendrogram. So this is the graph of the dendrogram. So as you can see, first we have started with the individual cluster for each data point. So we have created cluster for each data point. As you can see, this, and so on. Then after creating the cluster for each data point, then we will calculate the distance between each cluster. So as you can see, like in this cluster, we have find the distance between 7, 13, 20. Then after that, we will find which cluster are closest to each other, and then we will combine that cluster. So as you can see in this, these two clusters are closest to each other. Therefore, we have combined these two cluster. Then after that, these two cluster are closest to each other. So we have combined it. So we repeat this step to form only one cluster, which will be this. So now you can see if I cut the dendrogram at distance of 2000, which is this, so we will get two cluster, which will be this and this. And if we cut the dendrogram at the distance of 15,000, then we can get four cluster, which will be this, and this. So it depends on your cut how many cluster you will get. But the main question arises, which will be the optimum cut. So for optimum cut, we cut the dendrogram at the point where the horizontal line covers the maximum distance between the two vertical lines. So as you can see in this graph, we have cut it at the distance of 10,000 because it covers the maximum horizontal distance between the two clusters. As you can see, this will be the maximum in our every clusters. After this will be our maximum, then this will be our maximum. So therefore, we have cut our dendrogram at the distance of 10,000 and achieve 5 clusters like cluster 1, cluster 2, cluster 3, cluster 4, and cluster 5. So that will be the groups of our data points. And for top-down approach, which is divisive clustering, is exactly opposite to the bottom-up approach. In top-down approach, as the name suggests, we start from the top with all rows as one cluster and keep dividing the cluster unless every row is one cluster in itself. So for top-down approach, we will start with this point and then divide on the basis of the distance. In this, we will take the maximum distance to divide the clusters. So now you should be familiar with the K-mean and the hierarchical clustering. So now we will look into the DBSCAN machine learning algorithm. So for DBSCAN, it stands for the density based spatial clustering of application with noise. So do not get intimidated by this algorithm name. The more it sounds complex, the simpler it is actually. So first, let us look into some relevant terminologies for DBSCAN. So we have 5 terms that we use in the DBSCAN. First is our epsilon, second is our minimum point, third is our core point, fourth is our border point or non-core point, and fifth is our noise. So don't get nervous, they are basically very simple. So for epsilon, it is known as the maximum allowed distance from one point to the other data point for both of them to be considered in one group or cluster. So basically, it is just the perpendicular distance between the two data points. So for minimum point, it is the minimum number of points which should be present close to each other at a distance of the epsilon so that they all can be form a group or cluster. So basically it is the minimum or threshold value which tells us that in the group there should be minimum number of points. And for core point, it is that point which has at least minimum number of points near to it within the distance of the epsilon. And for border point or non-core point, they are the points which are not core points or that points in data which has less than minimum number of minimum points within its reach of the distance of epsilon. And for the noise, it is that data point which has no point near to it within a distance of the epsilon. So in DBSCAN, our epsilon and minimum point is also our hyperparameters, and we will look how to tune them afterwards. So first we will see the algorithm for the DBSCAN. So for algorithm of the DBSCAN, it start with one point randomly and found out whether it is a core point or not by checking the minimum number of points near to it by the distance of the epsilon. And then, if it is a core point, we will make it to a cluster and move to the next unvisited point to repeat our step 1. And if the number of points within the epsilon distance is fewer than minimum points, then we will mark it as our non-core point. And if the number of points within the epsilon distance is 0, then we will mark it as our noise. So after assigning the core point, non-core point, and the noise, we will combine all the clusters together whose data point are within the epsilon distance, and it is also known as our density connection. So this step will start a chain reaction, like if cluster 1 and cluster 2 are connected and cluster 2 and cluster 3 are connected, then it will automatically mean that cluster 1 and cluster 3 are also connected. Hence, we will combine all those clusters to make a single cluster. So we will look into the figure to understand this point. So this is the working of our DBSCAN. Like in this, we have minimum point equal to 3 and epsilon equal to 2 units. So first we will pick a random point like we have picked this and then draw a cluster at the distance of epsilon equal to 2 units. So we have drawn the cluster at the epsilon equal to 2 units, and then we will check the minimum points if they are in this cluster. So our minimum point is 3, but in this cluster we only have 1 point. Therefore, this will not be our core point. Then after assigning the value for this point, we will move to our next point, which is this. Then in this point, first we will draw the cluster of epsilon equal to 2 units. So we have drawn the cluster. This will be our cluster. Then after that, we will see if the cluster has minimum point equal to 3 or not. So as you can see, in this cluster, we have 4 points. Therefore, we will assign this point as our core point. So we will repeat this step for every data point. And as you can see in this data point, we have assigned it as a noise because in this data point, we have drawn the cluster and find out that there is no data point in the range of epsilon equal to 2 units. So we have assigned it as a noise. So after visiting every node and assigning it as co-point or border points or noise, then we will see if two clusters are merging with each other. So as you can see, this cluster and this cluster are merging with each other. This cluster and this cluster are merging with each other. So we will create a single cluster including all this small cluster and form a big single cluster, hence forming a group. So now you should know the basic working of DBSCAN, K-mean and hierarchical clustering. So now we will build the model and see the code for all these three algorithms. So for our model, our problem statement is that we have to create a predictive model which can cluster the same species of the flower with the help of its size. So to build any model, first you have to import our data. And to import any data, first you have to import the libraries import panda spd and then use read csv function to get our data. So we have stored our data in data areas and then we have printed the head of our data. So this is what our data look like. We have four columns: sepal length, sepal width, petal width, and the species of the flower. So basically, we have to group the species of the flower on the basis of these four variables. So after that, we will assign species to our target variable for the future reference, but we will not use this variable to group the data. Then after that, we will drop our target variable from our data set and use only these four variables in our models. So as you can see, we have dropped our species and assigned the remaining variable to the only predictor. And after that, we have printed the head of the only predictor. So now this is what our new data set look like, and we will use this to build our model. So as you all know that in supervised machine learning, we first split our data into training and testing sample. But in unsupervised learning, we do not want training and testing sample as we use the whole dataset and then create the clusters. So as you can see, we have assigned the only predictor values to our x, then our target variable to y. This is only for the future references. We will not use it to build the model. Then after that, we have printed some of the sample records. So as you can see in this is our sample record from 1 to 10 data. So as you can see, this is the same as our data set. So 5.1 equal to 5.1, 3.5, 3.5, 1.4, 1.4, 0.2. And in fourth row, you can see like 4.6, 3.1, 4.6, 3.1. So it is same as our data set. Then after that, first we will build our K-means cluster model. So to build the K-means cluster model, first we have to find the best number of cluster based on the inertia value. So what do you mean by inertia value? Basically, inertia measures how well our dataset was clustered by k-means. It is calculated by the measuring the distance between each data point and its centroid, and then squaring this distance and summing this square across one cluster. So a good model will be one with low inertia and have low number of clusters. So first we will import k-means library from sklearn.cluster. Then we have imported the plot from matplotlib.pyplot for our graph and then run a loop to find the best number of cluster based on the inertia value. So as you can see, this is the body of the loop, and in this loop, first we will assign the km equal to k means where I varies from 1 to 11. So we'll form the cluster from 1 to 11 and build the model and fit the data into our model, and then append the value of inertia into our array. So as you can see, this is the graph of our inertia values with respect to the number of cluster. In our cluster equal to 1, our inertia value is the highest, and in our cluster equal to 10, our inertia value is the lowest. So from logic, you can also visualize that the higher number of cluster, the lower the value of the inertia. But in this, we also want the minimum number of cluster and minimum number of inertia. So we will choose the number of cluster in 2, 3 or 4. So we have built our model with the cluster equal to 3. So after choosing the number of clusters, we have built our model with cluster equal to 3. So for init and init maximum iteration and tolerance, they all are pretty fixed values. And for random set, it just tells us that we pick our data in random order from our dataset. So after creating the model with n cluster equal to 3, we will predict our model with x and then print the array of the predicted clusters. So as you can see, this is the array of the predicted cluster. So we have grouped our data into 3 cluster, 2, 1 and 0, and our inertia is 78.85. So after that, we have printed our predicted cluster ID as we have grouped our data. So in this, we can tell that Sentosa is our second cluster and other species are of 0 cluster or 1 cluster. So now we will visualize the cluster using any two columns in our data set. So we have plotted our scatter plot with x-axis equal to sepal length and y-axis is equal to sepal width. And in our data, it will be our predicted cluster ID. So as you can see, we have created a model with three cluster yellow, cluster purple, and cluster green. But you can see there are some overlapping in our data when we are doing the cluster of three. So let us do the cluster of 2 to make this cluster 1 and this full data of cluster 2. So we have built our model again for n cluster equal to 2, and this all are pretty fixed value, and random set we can change into any data. Then after that, we have predicted our model using the X data, and now this is the area of our predicted cluster 0 and 1. But our inertia got increased. But it is logical as we have decreased the number of clusters, therefore inertia will get increased. If we do cluster equal to 1, then you can see our inertia got 507. And if we do cluster equal to 10, then run the program. So you can see our inertia got 21. Therefore, it is logical when we increase our cluster, our inertia got reduced, and when we decrease our cluster, our inertia get increased. So let's build the model for 2 cluster, and now we'll see 2 cluster, and it is pretty more good visualization than our previous model. In this, we can see there is no overlapping of our data. So from this, we can tell that we only need 2 cluster in our data set. So after seeing the code for the k-means, we will see the code for the hierarchical clustering. So this is our code for the hierarchical clustering. So in this code, first we have plotted the graph of one row and two columns. It means that we will plot two graphs. Then we have plotted the dendrogram to find the best number of cluster. In dendrogram, we use method equal to var because var minimizes the variance of the cluster being merged. Then we have plotted the graph into our first plot. Then after seeing the dendrogram, we have built our model with the n cluster equal to 3. So first let's see the dendrogram, how it look like. So this is our dendrogram for the data. So in this dendrogram, you can see that we have divided the cluster from the distance equal to 10. Therefore, forming three cluster, cluster 1, cluster 2, and cluster 3. But you can also see that they is somewhat overlapping in this cluster 2 and 3. And you can also see in this scatter plot, there is some overlapping in cluster 2 and cluster 3. Therefore, our best optimum, which say that we have to cut the dendrogram from the largest horizontal line. Therefore, we have to cut the dendrogram from this point, and therefore creating two cluster, cluster 1 and cluster 2. So now let's get back to our model. In this model, we have used the bottom-up hierarchical clustering, means that agglomerative clustering, and we have created three cluster with definity equal to Euclidean, where Euclidean is our distance formula, and linkage equal to what, where what minimize the variance of the cluster being merged. Then after that, we have predicted our data using the X and then plot the scatter plot, which you have already seen. So this was our scatter plot and this is our dendrogram. Then apart from dendrogram, there is one more method to find the best number of cluster for hierarchical clustering, which is Celoty coefficient. So in Celoty coefficient, the Celoty coefficient is calculated using the mean intra-cluster distance and the mean nearest cluster distance for each sample. The formula for the Celoty coefficient, which is equal to b minus a divided by maximum of a or b. And to clarify, b is the distance between the sample and the nearest cluster that the sample is not a part of it. So in Celoty coefficient, we get the value between the 1 to minus 1, where 1 is the best value of Celoty coefficient and minus 1 is the worst value of the Celoty coefficient. And in minus 1, you can imagine that our data is mixed in our data set and we cannot form any cluster. And values near 0 indicate that overlapping clusters. Negative clusters generally indicate that sample has been assigned to the wrong clusters. So now we have written the function for the Celoty coefficient, and from this function we get the value of the score and the cluster, and then we have appended the data into our Celoty score data. So now we will print our Celoty score data. So you can see this is our Celoty score data where we have got the score and the cluster. So in cluster 2 our score is 0.68 and in cluster 3 our score is 0.55, and if we go low in cluster like in cluster 9 it is 0.33, which tells us that they will be overlapping in our data set. So we will pick our best score, which is 0.68. Therefore we have to create only two cluster in our data set. So now after getting the optimum value for the cluster, we have again built our model for n cluster equal to 2. So now you can see our cluster, it will look like this. And in this, you can see our data is pretty good predicted as group 1 and group 2, and there is no overlapping in our dataset. And from dendrogram, you can also tell that if we divide the dendrogram by this line, we will only get two clusters. So now you should be able to write the code for the hierarchical clustering. So now we will look into the code for the DBSCAN. So DBSCAN was density-based spatial clustering of application with noise. And for DBSCAN, it works very fast with large dataset. And you should also remember that where k-means do not work, DBSCAN will work. So for DBSCAN, we have already discussed that there are two hyperparameter, epsilon and the minimum samples. So epsilon was the distance of the cluster and minimum samples equal to 4 tells that there should be minimum 4 data point in our cluster. So after assigning the hyperparameter db equal to dbscan epsilon 0.9 and minimum sample 4, we'll build our model. So first we have predicted our data using the x and then printed our head of the data. So this is the head of our data. And now you can see the scatter plot for the dbscan clustering. So this is what our model look like, and in this we do not have to assign the number of cluster, it will do it automatically. We just have to assign the value to the epsilon and the minimum sample. So it is pretty good in comparison to the k-mean and hierarchical clustering. So in most of the cases we use dbscan, and for dbscan we also can use Celoty coefficient to find the best hyperparameter as we use it in our hierarchical clustering. So for Celoty coefficient, the code will be this. So we have again written the function. First, we have defined the list of the parameter, like epsilon will go from 0.1 to 0.9, and this step will be 0.01. And minimum sample will go from 2 to 5, and the step will be 1, like 2, 3, 4, 5. Then after assigning the hyperparameter, we have run the loop and then find the Celoty score. So this will be our best Celoty score, which give us the score equal to 0.68, and the parameter will be epsilon 0.9 and minimum sample will be 4. As we have built our model from this only, so you can see our model was pretty good. Then after that we will look into one example where k-means will fail but dbscan will be successful in grouping the data. So our data set will look like half moon. So as you can see, to make our moon, we have imported the library import make moons from sklearn dataset, and from this hyperparameter this tells us that we have imported 500 dataset. So this is the data of 500 rows, and for shuffle it means that we have used the random order, and for noise equal to 0.1 it tells us the spread of the data, like if we use noise equal to 0.9, so this is what it will look like it is fully spread into one part. And if we use 0.01, then this is what it look like. It just tells us the spread how our data look like. So for our model we will use 0.1. So after this we'll first cluster this data using the k-means. So as you can see there are two clusters, cluster 1 and cluster 2. So therefore we have assigned our value and cluster equal to 2, and our other parameter are pretty same in every cases. So after that we have plot the scatter plot for the clusters. So this is what our scatter plot look like for k-means. So as you can see our k-mean have failed in grouping the data into two cluster, as it has grouped this cluster as 1 and this cluster as 2. But for DBSCAN the algorithm is different from the k-mean, and which is much better for these cases. So after that we will build our model in the DBSCAN. So we have built our model in DBSCAN, and where we got this value epsilon equal to 0.1 and minimum sample equal to 2. We got this value from our Syllogic Coefficient, which give us epsilon should be 0.1 and minimum sample should be 2. So now you can see the scatter plot for DBSCAN. So you can see DBSCAN work much better than the k-means in our moon dataset. So this is the case where DBSCAN works and k-means fail. So now you should be able to differentiate between DBSCAN and k-means and should be able to write code for all three algorithms, k-means, DBSCAN, and hierarchical clustering. So that's all for the video. So thank you for your time. For more amazing content and for more algorithm problems, do like and share the video.